All right, welcome back, everybody. So today we're going to be starting off going over this idea that we've kind of talked about before, but we really haven't solidified, which is that idea of polygons. Okay, so there's a couple of definitions that we need to work on before we can actually move on to talking about measures and stuff like that of polygons. And the first thing is we want to define, okay, well, what is a polygon? A lot of this stuff should be review, but I just want to kind of go over it really quickly. So a polygon is a closed sided planar figure. Okay, and that just means that it's closed, so we can't have something that looks like this, right? That's not a polygon, right? And it's got to be all in the same plane, so it can't just be kind of like one of those types of things as far as like kind of out in the third dimension and stuff. So really what a polygon kind of looks like, something like that. Even that would be considered a polygon because it's closed, it's sided, it's all on the same plane. Okay. Now we have this idea of what a convex polygon is, and that's the one that we're more familiar with. So a convex polygon is a polygon, so again, it fits all the same definitions of polygon, right? With no interior points, or with no interior vertices, sorry. Okay, so if we look at this example, right here, we can see that we have this interior point right here. And the reason we say it's interior, because if I connect all the vertices, right, we can see that this at this point right here would technically be on the inside of this polygon. So a convex polygon might be more like, a square that you're familiar with. Sorry, right? Or it could even be like, not a star. That's not right, Mr. Kiefer. Or it can be like, an octagon, something like that. Right? So like a stop sign, for example. Right? Those are kind of things that are more convex. Concave is essentially the opposite. It's a polygon with interior vertices. Okay. And so this example right here would be a concave polygon. So it looks like essentially the polygon is caving in on itself, right? Something like that might be considered a concave polygon. Okay. A regular polygon, all right, is a polygon with all sides and angles congruent. Okay, with all sides and angles congruent. So, for example, right, one that you're familiar with, right, would be a square. Right, all four sides are congruent. I've got 90-degree angles here, here, and here, right, and that would be an example of a regular polygon. Right, there's also an one that we've already seen, which is an equilateral triangle, right, which is again all sides are equal and all angles are equal as well. Pardon my horrible drawing. Okay. Now, what a diagonal is. All right, a diagonal is a segment, a line segment within a polygon. All right, so a segment within a polygon which connects non-adjacent vertices. Okay, so an example for our square, so I'll make it a little bit bigger, or rectangle even, right? If I have a rectangle here, right? Or sorry, if I have a square here, right, then actually I'll make it a rectangle, sorry. Then what a diagonal is essentially if I start here, I'll even use a different color. If I start here, right? So if I think about this point, these two points right here are adjacent vertices because they're right next to each other. And these two, right, are adjacent vertices. So the only one that it can connect to create a diagonal would be this segment right here. So this right here, which kind of cuts to the middle, right, this would be my diagonal. Okay? And the reason that we need to know what a diagonal is because we're going to use that, right, to kind of talk about different measures in a triangle or in any regular polygon. So what we're going to look at is specifically convex polygons. And so step one is what we're going to do is we're just going to take a polygon. So we have a pentagon here, for example. Right? And all I'm going to do is from one vertice, right? I'm going to draw, so I'm going to construct a diagonal from one vertex to every other non-adjacent vertex. So I'm going to start, I'll just start here. So if I can't, so again, I want to connect the non-adjacent vertices. So I want to create all the diagonals. So I'm going to draw a diagonal from here to here, and a diagonal from here to here. Okay, and again, I'm just kind of loosely doing this, but you can use a ruler if you need to. So now what I want to do is I want to figure out, okay, well, how many different, or what kind of shapes do I see in here? Well, I see 3 different triangles that I've created. So in this pentagon, I've created 3 triangles, okay? Now we want to use the triangle angle sum theorem to determine the total measures of the interior angles of the polygon. So essentially, if I'm looking at this guy, I know that the interior angle of the sum of this one is going to be 180 degrees. The interior angle sum of this one is going to be 180 degrees, and the interior angle sum of this one is going to be 180 degrees. All right, because for the triangle on the left, right, these 3 are going to add up to be 180. For the triangle in the middle, these 3 are going to add up to be 180. These are not congruent. I'm just showing you the angles, by the way. And then in the right triangle, these 3 are going to add up to be 180. And we'll notice that if I add up all of those together, right, so we have this one, and this one, we'll notice that those are going to give me my entire angle up top, no matter what the shape looks like. So realistically, I found I can use this to find all of the angles of this triangle. So if I add up 180, of this polygon, if I add up 180, 180, 180, right, that should give me, I believe it's 540 degrees, okay? So that tells me that in a pentagon, right, the interior angle sum is going to be 540, right? And so this is going to be how we're going to derive, right, the polygon or the interior angle sum for any polygon, okay? Now, oops, sorry, shouldn't have done that. Moving on. So now what we want to do is we want to find, okay, well, what's the measure of, if we had a regular polygon, for example. So let's just say hypothetically, right, that this guy was now, I'll use blue for this one. Let's just say now that this side, this side, this side, this side, and this side were all congruent, and more specifically, this angle, this angle, this angle, this angle, and this angle were all congruent. Okay, so if I wanted to do that, if I want to figure out, okay, well, what's the measure of each one of these angles, right, if they're all congruent, right, so what I'm going to do is I'm going to take this 540, right, and I'm going to divide it by the total number of angles in the polygon. Well, there was 5 of them, okay, and so 540 divided by 5 is going to give me 108 degrees, meaning that if this was a regular polygon, right, each one of these angles would be 108 degrees. All right, now to find the measure of what for exterior angles. So like a triangle, when we found if I think about an exterior angle, and we can see that each one of these guys right here is an exterior angle. If I want to find what the sum of their measures is, right, what I'm going to do is they're created just like a triangle, and although we can't calculate exactly what each one of these is just based upon this alone, right, this idea alone, what we want to do is we want to find the exterior angle measure of one exterior angle using the supplements theorem. So if, let's just say that this is a regular pentagon, okay, so this is going back to the same kind of idea that we had before. So let's just say this is regular, all of these are congruent, okay? Then what I'm going to do is I'm going to say, well, if this is 100, sorry, that should be blue. If this is 108 degrees, right, that would mean that each of these angles is 72 degrees, okay? So, and since they're all the same, they're going to be 72 degrees. So the measure of each one of these exterior angles is 72 degrees. Right? But now if I add them all up, you'll notice that we kind of get a cool little thing here. If I add them all up, 72, 72, 72, 72, 72, we're ending up getting 360 degrees. Okay? And this is what we call the polygon exterior angle sum theorem. Okay, so basically what you're going to do now, and we kind of just did that for a pentagon, so I'll go ahead and show you. On this next, oh no, that was supposed to be switched. I think I can find, give me 2 seconds. This should be, there it is. Okay, so on the second sheet, right, what we just talked about was we did a pentagon, and so we created 2 diagonals, All right, we know that there are 5 sides. We said that, here, let me move this down just a little bit so you can see it, what the top is. Number of diagonals from each vertex was 2. Number of triangles in the polygon was 3, because there were 1, 2, 3 triangles. We knew that the sum of their interior angles was 540, right? And the measure of one interior angle was 108. It's 108. The measure of one exterior angle was 72, and the sum of the exterior angle measures was 360 degrees. And so essentially our idea is what we're going to do is we're going to figure out how can I calculate that no matter how many sides a polygon has. So I'll start you off with the first 2, and then I want you to pause the video and I want you to actually work through the rest of these and see if you can figure them out. Okay, so triangle, we have 3 sides. We have diagonals from each vertex. Well, in this case, there's actually 0 because I can't draw one because each of the vertexes are non-adjacent or adjacent. Number of triangles, well, clearly there's only 1. The sum of the interior angles we said was 180. Measure of one interior angle if it's a regular only, meaning a equilateral triangle, is 60 degrees. Measure of one exterior angle if it's a regular one would be 120 degrees because it's just the supplement of the 60. And then the sum of the exterior angles, 120 times 1, 2, 3, would also be 360 degrees. All right, let's do the quadrilateral. Okay, number of sides is 4. I'm going to draw the diagonal. Again, we're going to do it from one vertex. Okay, so I picked this one, and that's the only non-adjacent vertex, so there's only one diagonal that we could create. Number of triangles in it was 2. Right? And so if there's 2 triangles, that means the sum of their interior angles, so this one's 180, this one's 180, the sum of their interior angles is going to be 360 degrees. Okay. Measure of one interior angle, if it's regular, meaning it's a rectangle, would be 90 degrees, which means that the exterior angle would also be 90 degrees. But then if I have 4 exterior angles, that's going to give me 90, 90, 90, 90, which would also give me 360 degrees. All right, and what I want you to do right now is I want you to pause the video, right, and try to recreate the rest of this. And then what you're doing for this last one, what you're doing for this last one, this n-gon, is you're trying to say, hey, you know what? If I've got just some general polynomial, right, with n number of sides, right, how can I create, or some polygon with n number of sides? How can I calculate the sum of the interior angles, so on and so forth? So essentially, you're going to be deriving the formulas for how to get this for any sided polygon. Okay, so go ahead and pause the video. All right, so hopefully, all right, this is the table that you ended up getting. Okay, and so what you can see is one of the patterns that we notice is that it doesn't matter, right, how many sides that it has. Right, my exterior angles will always be 360 degrees. And that's really nice because that can actually tell me, without ever having to find this measure of one interior angle, that can actually tell me what each exterior angle is by simply taking, hey, you know what, 360 divided by the number of sides there were, right? And that would give me each exterior angle. So if we look at the decagon, which has 10 sides, right, 360 divided by 10 is 36. And there we go, and our formula actually works, okay? And so that's kind of how you can figure out every exterior angle. Now, how we figured out each, all right, each other thing, so again, if we had the number of sides was n, right, we noticed that the pattern that we had is that the number of sides, or the number of diagonals that we could draw from each vertex was n minus 3, but then the number of triangles that we created was n minus 2. So whatever number of sides it is, minus 2, right, would give us the total number of triangles inside, which means if we took that number that we got, which in this case is n minus 2, we multiplied it by 180, and that gave us our interior angle sum. Then in order to find, and that's why our formula, so the polygon interior angle sum theorem, right, is right here. So this is the polygon interior angle sum theorem, which says that the interior angle sum of any polygon is the number of triangles, so n minus 2 times 180 degrees. All right, and then in order to find what each, for a regular polygon, in order to find the measure of each interior angle, all we did was take that number and divide it by the number of sides, or the number of angles that we had, or the number of vertices, and that gave us our interior angle sum, our interior angle. Okay. Now again, you can use algebra to kind of get to this part right here.